The problem of carbon dioxide emission is perhaps the biggest problem facing the planet. I would say maybe one of the biggest after war. And just to give you an idea of the scale of this problem, per capita in the US, we are responsible for about 15 tons annually. We need to come together as a society and on a global scale, we need to come together and make and combine our efforts, government, people, scientists, and bring awareness to this problem. However, it's very difficult to capture carbon dioxide from automobiles because you have to have a mobile carbon dioxide capturing system on board automobiles. And so this presents a challenge on its own because of the scale and the amount of carbon dioxide that is being produced per tank of fuel. I think that it is a lot easier, or ultimately will be a lot easier, to capture carbon dioxide from power plants. And here we have invented a new class of materials we call metal organic frameworks, or for short MOFs. These materials are constructed from inorganic components and organic components. And you can think about the inorganic component as a hub that is linked to other hubs by organics. And these components can be varied so that you can tailor the properties of the material to be selective to carbon dioxide. I should mention that carbon dioxide is mixed with other gases. And so we design these materials to be selective to seeking out carbon dioxide and storing it. This is one such MOF material we call MOF 177, and it is, as you can see, it's a nice crystalline powder, shiny powder. It is made from using a simple, environmentally benign process. It involves mixing of zinc oxide, which is the main component of sunscreen, and organic units, not very much unlike what we use in plastics. You put these two components together and you make this material, which is, you can think about it as a crystalline sponge. If you or I could see atoms, you could see that each granule is riddled with holes. These holes essentially are the residence of where carbon dioxide is going to be. And they are tailored in such a way as to seek out carbon dioxide, stores it in the pores as you would store something in a reservoir, concentrate it there, and once these crystals are full of carbon dioxide, then you can release it and concentrate it and pump it in a remote permanent storage location. If I take 1 gram of this material, okay, that would be about this high in this tube. 1 gram of the material, if I unravel this to its atomic scale, because the material is porous, it's like a porous sponge. If I was to unravel it, it would cover about 60 to 70 tennis courts. And they're constructed from metal oxide joints and organic linkers. The linkers essentially hold these joints together into extended structures that have many pores that are vacuous, essentially. The nice thing about these structures is that, as you can see, they're highly open structures. And suspended within this openness are the parking spots. These are the little red and white spots you see here that are stitched together to make the framework of the material onto which carbon dioxide can be bound and held into place. Each sphere that you're looking at is actually an atom that is stitched to other atoms to make the space within which carbon dioxide could be stored. Hopefully this makes the process of reducing carbon emission a more economical option for power plants.